Okay, so I believe where we left off last time was we were interested in looking at some of these questions about generative models, right? Okay, so questions 17 through or 16 through 20 deal with objective functions for generative models, and question 21 deals with what we're able to tractably do with different generative models. So yeah, these are the answers. I guess which of these objective functions did you have questions about? Yeah. Yes, evidence lower bound. So let's open up the variational autoencoder lecture. Okay, so the evidence lower bound is a way of approximating the maximum likelihood of objective for a certain class of models. And this is it. So we start with the log likelihood of our data, given by log p of x. And so the idea is that we're going to introduce what we will call a latent variable z and come up with, and the reason why we introduce that latent variable is so that we can train with this autoencoding setup, where z is that intermediate vector. And we can, these are just, the first three steps of this derivation are just identities, where we're, this is the definition of marginal probability from 1 to 2, and then we're just multiplying by something over itself. The really interesting part of this derivation is between steps 2 and 3. And what this says is, because the log function is a concave function, we can use an inequality called Jensen's inequality, which says that the expectation of the log of the expectation of a function of a concave function is going to be lower than the expectation of the log of the expectation of a concave function of a variable x is going to be lower than the function of the expectation. So on line 2, we have the function log of the expectation of q of z. And on the next line, we have the expectation of the function. And so Jensen's inequality says that that is going to be less than or equal to that. And you can imagine it, the easier way to think of Jensen's inequality is just if you think of a concave function and then you draw a line between 2 points, that line is going to be lower than the function itself. Yeah, and so basically then with some more rearranging of terms, this lower bound reduces to a likelihood term where we are maximizing the likelihood of x given z, and a KL divergence term where we are making sure that our z vector matches a normal distribution. And so, yeah, so then when we're actually training our model, we maximize this lower bound. So we're maximizing the likelihood of x given z, as well as minimizing the KL divergence between q and p, q of z and p of z. And kind of in effect, because we're maximizing the lower bound, the hope is that that will also maximize the thing itself, which is the probability of x. So in short, we are trying to maximize a lower bound on the log likelihood. So it's very, very similar to maximum likelihood, except it's just not exactly maximizing the log likelihood. Okay. That's the evidence lower bound. Yeah, and so the elbow, the evidence lower bound, applies to variational autoencoders, and then it also applies to diffusion models. And the derivation for the evidence lower bound for diffusion models is similar to the derivation for variational autoencoders, but it's a little more hairy, and so we didn't do the whole derivation in class. Okay. Yeah, cool. Yeah, so the question is, what is the definition of an objective function? Yeah, that's a good place to start. So an objective function is the same as a loss function, and it's some measure of success of our model. And specifically, we want it to be a differentiable measure of the success or failure of our model, because we want to be able to back propagate that success to change the parameters of our model. And so yeah, and usually an objective is kind of a mathematical version of some idea that we have in our heads. And so there can be, and it's a lossy approximation often. And so a lot of the time we're going to be maximizing the likelihood that will be our objective function. But there are other cases where in Bayesian learning, where we will try to maximize the probability, try to find the most likely parameters given x, which is a slightly different objective. So maximum likelihood is maximizing probability of x given parameters. Bayesian learning is maximizing probability of parameters given x. So yeah, basically an objective function is a mathematical version of some real world objective that we want to achieve. Okay. Let's talk about question 21. I don't think this is one that people asked about specifically, but I think it's a good one to go over. So we have five different types of generative models that we've talked about. We have autoregressive generative models. Does anyone remember an example of an autoregressive generative model? Yeah. Yeah, a transformer can totally be used as an autoregressive generative model. Same thing with an RNN. And this isn't something we covered in a ton of depth, so I think I'll just do some writing on the board to give you an example. So with a generative model, we want to maximize the probability of x1, the joint probability of x1, x2, etc. And we want to either do density estimation or sampling with that model. And the chain rule of probability says the following. We can take a joint probability distribution, and that will be equal to the product of from I equals 1 to n. We'll expand this out all the way to xn. Of the probability of xi given x1 all the way up to xi minus 1. And so basically what that says, if we're going to translate this into the transformer setting, and we want to either do density estimation or sampling for a sentence, our x1, x2, all the way through xn will be words. So someone give me a sentence. How are you? Okay, so how is x1, r is x2, u is x3. So in that case, we could, the product rule says that the joint probability distribution of how are you, or the joint probability density of how are you is the probability of how times the probability of r given how times the probability of u given r and how. So basically the probability of each successive item conditioned on the things coming before it. And so, in order to get this to do density estimation with an autoregressive model, we would take the probability of how, which in this case, we would be given the start token. And then we can pass how into our transformer and get the probability of the word r. And then we can pass how and r and get the probability of u, and then multiply those three probabilities together. And that gives us the exact probability of the sentence, how are you? Okay, so then are we able to use autoregressive generative models for density estimation? The answer is yes. We just talked about how to do it, right? So we basically get the probability is of each successive item conditioned on the things coming before it. Can we use autoregressive generative models for sampling? Can we sample from a transformer? Can we sample new text? Travis is saying yes. How would you sample from an autoregressive generative model, Travis? Exactly, totally. Yeah, and that's exactly how you do it. So for those who didn't hear, you can sample the probability for the first token. So suppose we sample across all of our probabilities, and the first word is the, because the is a common word to start a sentence. And then we can pass the into our model and get probabilities for the next token. Let's say it's the word black, and then we can pass the black and into our model and get the word ship, and then pass it in, and we sample the word sailed, et cetera, et cetera. So that's how you use an autoregressive generative model for sampling. Okay, so that's autoregressive models. And we can use them for both density estimation and sampling. VAEs, we can use them for sampling. Does anyone remember how you sample from a VAE? Yeah, so going back, Travis, yeah. Yeah, the question is, what is the purpose of density estimation? What is how is it useful to get the probability of the joint probability of the data? So one example is there are certain sampling algorithms that use the what is the word? The density. They use the value of the probability density. So like Monte Carlo sampling, Markov chain Monte Carlo sampling uses the probability density. Yeah, other reasons. Yeah, so you get the probability of that sentence. Yeah, another thing that allows you to do is compare the probability of two different items from your data set. So you could take the sentence, how are you, and take the sentence, I eat paint. And hopefully, how are you is going to be more probable than I eat paint. And so that can be useful for detecting kind of whether something falls into your distribution or not. Yeah. And there are probably other applications for density estimation, but I can't think of them off the top of my head. Okay, so any other questions on that before we move on to VAEs? Okay, so VAEs. So it sounds like people didn't remember how to sample. Does anyone remember the general setup of a variational autoencoder? Yeah, Joseph. Exactly, totally. Yep. So we're going to, yeah, like Joseph said, have a normal distribution, and we want to map our data into that normal distribution and back out of that distribution. And so that's the autoencoder part of it. So we have on the left-hand side, our data X, in the middle, our latent space Z, and then on the output, we have the reconstruction of our data X. And yeah, so in order to sample from a VAE, the whole point of this was to map a tractable distribution. Do you know what I mean when I say tractable? Yes, Spencer? Yes, computationally feasible. So tractable just means something that we can sample from reasonably fast, and also do density estimation reasonably fast. So yeah, cool. Right. Great question. So the question is, using the diffusion lab as an example, we don't have the computational resources to actually train it in this class. Would that be considered tractable? So usually when we're talking about tractability, we're referring to inference, so predicting on new data. And so it's kind of a given that training is never going to be easy, but hopefully inference does not take like as long as training, right? And so hopefully inference will just be a single forward pass through our network or something like that. When we say intractable, usually that refers to like computing an integral over the entire data set. So basically running a forward pass over our entire data set and summing it up, something like that. Yeah, so the normal distribution is very tractable. We can sample from it very easily. And so to sample from a VAE, we will sample a normal vector, and then from the normal distribution, and then pass it through the decoder of our VAE to get a sample from our data space. Any questions on that? Pretty simple. Sample a Z vector from a normal distribution, and then pass it through the decoder. Now VAEs do not give us the log likelihood, because if you remember, we did not train them using maximum likelihood. We trained them with that variational lower bound on the log likelihood. And so with VAEs, we can get a lower bound on the likelihood of our data, but we cannot get the exact likelihood of our data. Any questions on VAEs before we move on to flow models? Yeah, Dane. What it is about them that makes them variable? Oh, variational autoencoders. So I believe the term variational comes from the term variational inference, which refers to models that use this variational or this evidence lower bound objective. I believe. I'm not. So Yeah, this is not my main field of expertise, but variational inference is also related to Bayesian learning, which I mentioned earlier. Yeah, and so the lineage of VAEs comes from Bayesian learning, and I don't exactly have I'm not super prepared to answer that question, but if you're interested, those are kind of some keywords that you can use to further explore that. Okay, flow-based generative models. Okay, do you remember the big idea behind flow-based generative models? They were very similar to VAEs, but so there's one word that's missing before this flow-based that's often included and is probably the most important part. So yes, we did have the negative log likelihood, but that's basically the same as the log likelihood. But yes, you're right. We did train with a maximum likelihood objective or a minimum negative log likelihood objective. And the whole idea behind these is that these were invertible neural networks, which is really like the powerful idea behind them. And we structured them to be invertible by using these affine coupling layers that allowed us to reconstruct the inputs from the outputs. And that resulted in a Jacobian matrix that was a Jacobian matrix for which we could, that was triangular. So we can compute the determinant very easily and thus kind of go back and forth between X and Z space without any issues. So basically a flow-based generative model is just an invertible version of a VAE where the encoder and decoder are the same thing, and to go back and forth between X and Z space, you just reverse the model. Okay, and so because of that, we are able to do density estimation. Any idea with if we can map X's to Z's and back and forth, how might you do density estimation for a given image X? Michael, yeah, you want to give a shot? Run it backwards through your network. Okay, so you run it backwards, you get a Z. And then what do you do with that Z? So we've taken a sample from our data set to a sample from, you're really close, to a sample from the normal distribution. Close. So a normal distribution, we can do tractable density estimation. So we can just take the value of that Z vector, the value of the normal distribution at that Z vector. The Gaussian function takes as input a vector X. We put Z in as that, and we can get out a probability. And so to sum that up, to do density estimation for flow-based models, we take an X, pass it backwards to get a Z, and then get the probability of a Z vector under a normal distribution. Okay, how about for sampling? Maybe? That is exactly right. Yeah, so, well, yeah, you finish what you're going to say. Yeah, so sample a random Z vector, and we want to get a random X. So then what would we do with that Z vector? Pass it forwards through the network to get an X. Exactly, yeah. Yeah, so that's how you do sampling with a flow-based model. Yeah. Yes. Mm-hmm. Good question. So the question is, was there a special way that we guaranteed that that the Z space was a normal distribution in flow-based models? The answer is, I'm sure the answer is yes, because they work, but I don't remember exactly how. Let me pull that up right now. So I believe that the answer is that the way that we enforce Z being from a normal distribution is that we maximize, our objective is to maximize the likelihood of Z under a normal distribution. So it's right there in our objective function. Okay. All right, so next we have diffusion models. So diffusion models, we have on one side, we have our data, x0. And on the other side, we have our, again, tractable distribution Z. So, and that is again going to be a Gaussian. So hopefully it's getting pretty easy at this point. Any ideas how we would sample from a diffusion model? Yeah. What was that? Yep. Sample a random vector Z and then pass it through our denoising model. And there were two ways that we talked about that you can do this. One is you use our denoising diffusion model to denoise that Z vector into a sample from our distribution at every single step. So if we trained with 1,000 steps, we denoise from 1,000 to 999, 999 to 998, and so on. So that would be 1,000 steps, through 1,000 passes through our diffusion model in order to get one sample. But we found out that there was a better way to do this, right? And you guys took a look at this in your lab. You remember the better way than doing 1,000 denoising steps? Brianna, did you say something? Exactly, taking bigger jumps. Yeah, so we took a look at that model, at that paper, the DDIM, Deep Diffusion Implicit Models, that showed that we can, basically by using a different coefficient, alpha sub t, we can skip steps in that denoising process and use as few as 10 steps to sample from a process that took 1,000, that divided training up into 1,000 different steps. Okay, good. And then density estimation on diffusion models. This one is kind of tricky. We did not talk about this at all in class, but I just thought I'd put it on here so that you are aware. So for diffusion models, one way you can interpret them is as a stochastic differential equation, where there is basically an ordinary differential equation that maps each sample x to a sample z, plus some noise term, which turns it from an ordinary differential equation into a stochastic differential equation. And so it turns out that for every diffusion model, there is every stochastic diffusion model, there is a deterministic, what's called a probability flow ordinate ODE, or probability flow ordinary differential equation that allows you to map exactly from a sample X to a sample Z. And if we can do that, that's exactly like flow-based generative models, and we can just get the probability of Z under a normal distribution. There's an entire paper that talks about how to do this, which we didn't take a look at, but I just wanted you to know that you can use diffusion models for density estimation. Okay, so then GANs, we can do sampling. Why can't we do density estimation? Any thoughts? So I mean, we are in a GAN, as a review, we have a generator and a discriminator. What does the generator map? What is the domain of the generator, and what is the range of the generator? What does it map from, and what does it map to? Yeah, Tim? Yeah, so yeah, great. So it takes as input a sample from a tractable distribution, like a normal distribution, and maps it to a sample from our data set. Yeah, and so and then the discriminator takes that sample from the data set and says whether it's real or fake. And so we have a way of sampling from GANs, but not a way of reversing them to get the density estimation part. There's no way to go from an image and get a Z vector and then evaluate the probability of that Z vector. Any ideas of like maybe how we could make density estimation possible with a GAN? Yeah. Oh, interesting. So kind of use an auto-encoding objective on, so go from Z's to X's back to Z's, as opposed to, it's kind of like a reversed variational autoencoder. That's a really interesting idea. Yeah, that would be interesting to try. Yeah, and another option is maybe, what if we made the generator an invertible neural network? So that we have an invertible mapping between these X's and Z's. That might be a way to make it possible to do density estimation with GANs. Okay, so yeah, these are, hopefully it was helpful to go through these 5 classes of generative models. If you're aware of each of these models, how they work, how you sample from them, how you use them for density estimation, you will probably be ahead of like 95% of the people out there who, even among people who understand deep learning, I would say that like how you use each of these models for sampling and density estimation is not very well understood. So that'll be a good thing for you if you can understand those things. Yeah, Joseph. Yeah, good question. So the question is, why would you use a model that you can just use for sampling? And the answer is, I mean, if all you care about is sampling, and also a lot of these models that only allow sampling tend to do better. So I mean, for a lot of the time, for a long time, GANs were the state of the art for generating images for sampling from distributions, and so that is why you would use a GAN instead of VAE or something like that. But of course, as I mentioned before, kind of the ranking of these and which is the best it's kind of a rotating ranking of which of these generative models is the best. So it's good to know all of them and to see which is best suited for your situation. All right. Well, that is it for today. I'll see you on Friday.